So, last video I covered some of the basics of hashing, what it is used for, and desirable characteristics in hash functions. This time I want to cover more about how hashing works. This will be by no means an in-depth discussion, that could be an entire book or even a series of books. Instead, I want to explain some of the basic principles and techniques behind how hash functions work, by looking at how we might develop a basic hash function and what we want a hash function to achieve. In general, in a hash function, information from the input is lost so that we can form a constant length hash. The most basic hash you could create is to truncate your input to the length of the hash, and to deal with cases where the input is shorter than the hash, you could just pad it with zeros. A major downside of hashing like this is that it is very possible to have two slightly different outputs generate the same hash. Let's take a quick look at an example, defining our hashing algorithm as truncating the input to 10 characters, or padding it to 10 with zeros. We will now generate hashes for the following inputs based on that setup. This gives us the following hashes. Here we can readily see that all the first 5 hashes are different, but these hashes would also indicate that the 5th and 6th inputs are the same. This is because the hash function does not use the entire input. This is where the equation in the thumbnail comes in, and yes, it is a basic hash function with an input n, and the hash is the remainder when the input is divided by 10. We can express this in a more general way as n mod m, where n is the input and m is some number, but I'll expand on the effect of changing m in a minute. We can improve our hashes by using this function, but for the sake of simplicity, instead of using the values I used before, let's take some random numbers as inputs to this function. Let's say these numbers. While I have used numbers here for simplicity's sake, you could still use this for the previous examples, you just have to convert the inputs into some numerical form. The hashes for these inputs with this function are as follows. So as you see here, we already have an improvement over the last hash function in that the last 3 similar values all have different hashes, but now we have a different problem. 3 and 293, two very different numbers, have the same hash. The reason for this becomes apparent if we just take the numbers 1 to 30 and calculate the hashes of those numbers, and this gives us the following. So we can see here that basically anything ending in 1 has a hash of 1, anything ending in 2 has a hash of 2, and so on. Now a simple solution could be to divide by 100 instead of 10, and this would mitigate the issue to some extent with the new hashes as follows. This is where the m in n log m I mentioned before comes in, and this basically means that we can control the length of the hash by changing m. A larger m will generate a longer hash, a smaller m will generate a smaller hash. While this is an improvement over the old hash function, unfortunately this method still does not produce a characteristic that we often desire in hash functions that I mentioned in the first video on hashing, and that is the characteristic of irreversibility. With the current hash function we are considering, it is very easy to work out the possible inputs that would produce a given hash. For example, we could take the hash 5 and immediately work out the set of inputs that produces this hash. In this case, it's 5, 15, 25, 35, and so on. While this pattern and predictability is only a small issue where hashing is used to ensure data integrity, it is a much bigger issue in security applications like password authentication. So what we need is a hash function that cannot be reversed and used to work out the input, and I hope to explain why another time when talking about hashing and password authentication. This is where another thing I mentioned in the last video, the avalanche effect, comes in. To quickly demonstrate this effect, here are those same numbers 1 to 30 hashed with a hash function also mentioned last video, SHA-256. Aside from the fact that these hashes are much longer, we can also observe something else. Each one is very different from the last one. These differences are the manifestation of the avalanche effect. This effect is one of the most commonly sought after features in hash functions, and it is closely related to another effect called the butterfly effect. The butterfly effect is where in a system a small change to the input has a large effect on the output. As a simple example of this, consider the equation y equals x squared. In this case, let's use x as our input and y as our output. If we graph this for when x is greater than 0, we get this curve. As x increases, y also increases, but not at the same rate. Let's start with x equals 0. At this point, y also equals 0, but increasing x to 1 gives us y equals to 1. But increasing x to 2, we get y equals 4. At x equals 3, y equals 9. We could go on with x equals 4 and y equals 16, but you get the idea. As the x value, the input, in this case, gets larger, the y value, the output, also increases, but not at the same rate as x. And this effect gets even more pronounced as x gets larger. Let's take x equals 100 and x equals 101. Here, the y values are 10,000 and 10,201, respectively. With x being 2 and 3, the difference between the outputs was 5. Here it is much larger, 201 to be precise, and this is only a fairly tame example. Using the values 2, 3, 100 and 101, let's just for fun change the equation slightly to y equals 2 to the x. Now our values are very different and the effect is much more pronounced. Make that much more pronounced, and bear in mind that this is a very small and simple system. Anyway, that was a bit of a sidetrack. Let's get back to the avalanche effect in hash functions. In general, to create a good irreversible hash function, we apply a variety of techniques, and while I am not going to explain SHA-256 right now, I will mention a couple more key principles that are important to good hashing, and in fact to cryptography in general. These principles are called confusion and diffusion. Confusion is where each bit of the hash is dependent on several parts of the input, and there is no way to find the connection between the parts of the input based on the hash. Diffusion, the other key principle here, is where changing one bit of the input changes approximately half of the bits in the hash. Anyway, that's all I'm going to cover for this time, but next time I hope to go over an application of hash functions.